Okay, so we would see another theorem today, that let T, capital T, this semigroup, okay, be a C0 semigroup, and let A be its infinitesimal generator, then followings hold, okay. For any x in capital X is the Banach space, correct? So capital TT is C0 semigroup on this Banach space capital X, correct? So for any small x in capital X, limit h tends to 0, 1 over h integration small t to t plus h capital T of Sx ds is equal to capital T of small t x. Okay. So this criteria is, property is immediate actually because of the continuity. If this is a continuous function, and that is true because it is a C0 semigroup. So if it is continuous, then of course if you integrate t to t plus h, and then that integration you divide by h and take limit h tends to 0, you would get the value at t. Okay, so that is actually immediate. It is now property B, for any small x in capital X, okay, this integration 0 to small t of Sx ds, this integration, so this would be a vector, a point in capital X, correct? Because small x is there, ts is a linear operator, you are getting a vector in capital X, and on that you are doing this integration 0 to small t, so it would be actually a vector in this. So but this statement is saying that something more. It is saying that this vector is not only in X, it is also in the domain of A. What? Because domain of A could be a subset of capital X. It need not be everywhere, correct? So this is saying that, okay, after integrating the application of the semigroup on a vector, whatever vector is there, okay, in capital X, okay, so and then if you integrate some, then that integrated one, whatever you get, that would lie inside the subspace of domain of the generator. Okay, so this needs a, this is not obvious clearly. Yes, one can think that, okay, since integration is there, possibly some kind of sort of smoothness has occurred, so we are getting some sort of regularity. Indeed, that is the kind of argument that is the kind of reason, but we need to prove it systematically. So it is in the domain of operator A. Now this result is saying that if small x vector is in the domain of A, that means it is not anywhere in capital X, but actually in the subspace of that, the domain of A, if it is there, so then we can say that, okay, capital TT of X is also in the domain of A. Okay, this is something which is not true otherwise, correct? When small x is not in the domain of A, but in capital X, we cannot conclude this. Okay, we cannot conclude this. However, if small x is in the domain of A, then application of the semigroup on small x is in the domain of A. So one can compare these two statements. Here in this statement B, we got that for any small x in capital X, the application of the semigroup on the vector small x, but integrated on any interval 0 to t, doesn't matter what t is, any is arbitrarily small or large, whatever, then that would lie in the domain of A. But if we want something more, that we want not the integration but just the t of x to be in the domain of A, then we need to assume that x is in D of A. Okay, and so if x is in D of A, ttx is in D of A, not only that, we can also conclude that the derivative of TTX, because TTX okay, is in domain of A. So we can talk about the derivative ddt, derivative of TTX, that would be equal to ATTX. I can talk about ATTX because TTX is in domain of A. Since TTX is in the domain of the operator A, so A of TTX is meaningful. So this is equal to ATTX, and not only that, that value is same as, so this vector is same as TT of AX. This is also meaningful because small x is in the domain of A, so AX makes sense. Okay, so we get this thing. Next, we start the proof. The part A, okay, so as I have earlier mentioned, this part A is easy. This is trivial actually. This is followed by the C0 semigroup property, because this is a continuous map. For any continuous map, this is true. So this follows from continuity of this map small t to capital TT of x. Okay. Now for part B, we need to show that this whole thing is in the domain of the operator. To show that this thing is in the domain of operator, we need to apply this th minus I divided by h, that operator, and we have to show that that limit exists. Okay, that is the way to show something is in the domain of operator. So we do that. We take this fraction 1 over h, t of h minus identity. So this fraction, okay, so this operator we apply on this vector 0 to small t ts dx dx. Okay, and then after applying this, what we get is that this 1 over h, t of s plus h, this s is there, h is there, the composition of ts and th is t of s plus h, okay, x minus identity, so minus ts. Okay, so this operator, okay, composed with ts gives me t of s plus hx minus tsx ds. Okay, so from here now I can write down this as two different integration. One is from say s plus hx ds. So here I can do substitution of variable to make it h2 t plus h s. Okay, another is 0 to t. Okay, so when h2 t plus h, that we can write down as 0 to t plus h by adding subtracting 0 to h, this thing 0 to h tsx ds. So if this integration 0 to h, if I add here and then subtract, I'll get 0 to t plus h, and here it is 0 to t. So that difference would give me t to t plus h tsx ds. Okay, so the way to get this is that write down this difference as difference of two different integrations, and then subtract, okay, those integrations, and then you get into 1 over h t to t plus h tsx ds minus 0 to h tsx ds. So here what we have obtained is that a very small tiny interval, subinterval t to t plus h. Here also tiny subinterval 0 to h. Okay, but 1 over h is also there. Okay, so now we apply the first part A. Okay, so part A, so since this is continuous, so this limit converges to tt of x. Okay, so this converges to tt of x, and this converges to t0 of x, but t0 is identity, so it converges to x. So we get that this thing converges to minus tt of x minus x, okay, as h tends to 0. So what did you get? We have obtained that this limit exists. Okay, as h tends to 0, this limit exists. So since this limit exists, that means this from the definition of the domain of operator of the generator of the semigroup, we know that this vector is in the domain of the infinitesimal generator. So integration 0 to small t tsx ds is in the domain of A. Okay, so that is the proof of B part. Okay, next we see the proof of part C. Let small x is in the, so this is a short notation. I mean, small x is in the domain of A, okay? So like DOM, dome of A, okay? Domain of the operator A, as TT is in BLX, that is, bounded linear operator of X, okay? So we can get the following thing, that here in the C part, let us recall what we want to prove. We want to prove that if X is in the domain of A, then TT of X is also in the domain of A. So we need to apply that fraction here and need to show that the limit exists. Okay, so we do that. So 1 over h th minus I, exactly as we had done before, 1 over h th minus identity of tt of x. We need to show that this limit exists as h tends to 0. So this thing I can rewrite as t of t, because they commute these operators. T of t times t of h minus I divided by h x, okay? So now, since x is in the domain of A, so this limit exists as h tends to 0. So this limit goes to Ax, and here TT is a bound linear operator. If this goes to Ax, TT of this thing would go to TT of Ax, okay, due to continuity of capital T. So as h tends to 0, this thing goes to TT of Ax. Okay, so what does it imply? It implies that TTX, this thing, this whole limit converges, so that means TT of x is in the domain of A. And not only that, here that when this limit exists, okay, this left hand side is nothing but A of TTX, correct? A of TTX. So A of TTX is equal to right hand side, that is TT of AX, okay, TT of AX. So that is the condition of this, that if x belongs to dA, then TTX belongs to dA. And in the D part also, like, A TTX is equal to TTX. So this part also partly we have proved. However, we have not proved that that is actually the derivative, okay. So if we can prove only one part of this, other part would be obvious. Why? Because already have shown that these two things are equal. Okay, so ATTX is equal to TTAX. Now for the D part, what we do is that we take 1 over h t of t plus h minus TTX. Why do we do that? Because we need to show it is differentiable. TTX is differentiable. To show it is differentiable, we use the first principle. In the first principle, we take that to show some function is differentiable, we need to take the rate of change, okay? So here we take first positive side, okay, right hand derivative. So t plus h is positive here. So capital T of t plus h minus tt of x divided by h. So now here, since capital T is a semigroup, so capital T of t plus h is equal to capital TT composition TH. So we can take capital T of t common. So after taking common capital T of t, what we are left with is capital T of h from here. And here I would be left with an identity matrix, identity operator. So after taking T of t common, we have T of h minus identity divided by h, okay? However, since x is in the domain of A, so this limit exists and this converges to Ax, and TT is a bound linear operator, that means it is continuous. So this thing would converge to TT of Ax, okay? So what we have obtained is that this thing converges to TT of Ax, okay? This limit converges. Since this limit converges, we cannot straight away say that this is differentiable, because it's the right hand side limit, right? H is essentially taken as positive, okay? So we can conclude that the right hand side derivative ddt plus of TTX exists, and that is equal to TT of Ax, correct? So TTAX. Okay. Now we should consider the left hand side derivative also. Okay, so we do that. So for left hand side derivative, what we do is that 1 over h tt of x minus t of t minus h x. Okay, for any positive small t, we write down this. Of course, small t cannot be less than h or 0, then it will be negative, but that is not defined here. So this is written only for small t, which is h or more. Okay, for h or more. So it doesn't matter. One should view it in the following manner. You consider any positive small t, and for that positive small t, you find out one h which is even smaller than that, and then consider this difference. Make sense? Good. So 1 over h of this ttx minus t of t minus hx minus tt of ax. So what do we need to do? We need to show that as limit h tends to 0, this thing goes to tt of ax. So for that, what we do, we just take the difference and want to show that this whole thing goes to 0. Okay, so so this difference is rewritten as, so here we take common t minus h. So since we have small t here, so small t is t minus h plus h. So t minus h we take common, and then we are using semigroup property. Okay, so capital T of t minus h taken common. So here we have capital T of h here, and then minus identity from here, and then whole thing. So this there is a typo here, so this 1 over h should have been outside here, and this is an extra bracket here. So this whole thing is that fraction what we are looking for, times x minus capital. So here I had tt of ax. Instead of writing tt of ax, I add and subtract this quantity, that is t of t minus h ax. So here I have t of t, but I am writing t of t minus h. Since I have subtracted it, I must add also. So I add here t of t minus h ax. So the same thing I have subtracted and then added, and then I have this minus tt of ax. Okay, so I have from this I have these two differences. Now we see that, okay, this difference, okay, capital T of t minus h ax minus capital T of ax. So this difference, so the norm of this goes to 0. Why is it so? Because x is in the domain of A, so ax is a member in the Banach space, and then this member is fixed here, both the places, and here T capital T is a C0 semigroup. So as h tends to 0, so this thing would converge to here. So norm of these things goes to 0. Okay, so here from this we know that this part would be 0. So now norm, if we apply all these sides, so norm of this thing is less than or equals to norm, and then use the triangular inequality, norm of this plus norm of this. So this part goes to 0. So just I need to show that this norm also goes to 0. Okay, so let us look at this capital T of t minus h here, and here it is correctly written, capital Th minus identity, okay, bracket, okay, times h minus, here I have taken t of t minus h common, so I have only ax here. So from left hand side I have taken common t of t minus h both sides. So I have this thing. Okay, so now norm of composition of operators is less than or equal to product of the norms. So using that we write down this is less than or equal to norm of capital T of t minus h times norm of this quantity, norm of 1 over hth minus identity x, okay, divided by h minus ax. However, x is in the domain of A. That means as limit h tends to 0, this thing converges and converges to ax, and ax is here. So this converges to here. So that means this whole thing converges to 0 as h tends to 0 in this norm. Okay, so this is not the operator norm. This is the Banach space norm, correct? So in this norm, this goes to 0. So that was our goal, correct? So now we know that, okay, this term, norm of this term also goes to 0, norm of this term also goes to 0. So norm of this term goes to 0, or in other words, that this is the left-hand side derivative. So d minus dt minus of ttx. Okay, so that exists because that limit converges, and where does it converge? This derivative. This is the answer, tt of ax. So right hand side derivative also exists, and that is ttx. Left hand side exists, that is ttx ax. So the derivative exists. Okay, so hence d holds. Okay, so that is the end of the proof of the theorem. So let us look at the theorem again. So this is the end of the theorem, and this the importance of the theorem would be now clear, because here what we have done is that we have obtained one Cauchy problem actually. So imagine that I don't know what is here, it is unknown. I have just a Cauchy problem, ddt of something is equal to a times of same thing, the ttx is here. Okay, imagine that ttx is unknown. Okay, so then it is a Cauchy problem, okay, given the operator a. Now the goal is that find out the infinitesimal generator, identify capital A as an infinitesimal generator of a C0 semigroup. If you can, then that semigroup acting on X would be the solution of the problem. Okay. And then if your initial condition is also here that that T0 of X. T0 of X is X exactly, and that is in the domain of A, correct? So if in this Cauchy problem the initial condition is also that initial vector is not anywhere in the Banach space but in the domain of A, then this would help us to solve one abstract Cauchy problem. Okay, so that is the importance of this theorem. So we summarize that thing here in this slide. So consider a homogeneous initial value problem. Okay, we often call it this as a Cauchy problem. Sometimes we call this initial value problem. But it is important that we say that it's homogeneous. Why homogeneous? Because the unknown appears here. Okay, and there is so it is a linear function. Okay, it is a linear equation, and there is no other source term. Okay, so this is the main reason that why are we consider this semigroup theory approach. Okay, why? Because in the whole course we were looking at some partial differential equations, and we were trying to solve that using probabilistic method. In this part of semigroup theory, we are not using any probability theory. However, we are using the semigroups, and in the probability theory part, what we have seen that we have used the semigroup generated by some Markov process or Brownian motion. Okay, so using those we have solved some partial differential equations. So here in this part, we are considering abstract Cauchy problem where the generator A need not be half-time Laplacian, because if it was half-time Laplacian, then it was like the parabolic the heat equation, parabolic PD, which we have solved. And for that, the semigroup, I should look at the semigroup which is coming from the Brownian motion. But in this section, we are considering any arbitrary type of operator. Okay, so this is abstraction of the things what we have already discussed for more general setting. So this is really important for research applications, because when we encounter new research problems, it is not necessary that the Cauchy problem what we will be dealing with, that the operator that is just one of the half times Laplacian or some very standard operator, but it could be very complicated. But then the approach is that can we identify that operator as infinitesimal generator of some C0 semigroup. Okay, so So here this is a statement that if you consider this homogeneous initial value problem, so if A is the infinitesimal generator of a C0 semigroup T, okay, then the Cauchy problem has a solution, and the solution psi of T is capital T of T comma capital T of X. Okay, what X? The X is the initial condition. So given starting the X, so this is the solution. So solution is also very easily written here. However, the problem happens that most of the time the initial condition is not so good. That means that it may not be in the domain of the operator. So that is the kind of discussion we would be dealing with, okay, in the rest of the part of this of the course. Okay, and here, to understand this thing, let us recall another example which we have seen just a few lectures back. I'm not giving the proof of this because essentially I have proved this part actually in the earlier theorem. It's just rewritten part of this, or you can say this is a very trivial corollary that follows from the previous theorem. Okay, so we look at this example that we have already seen that for the translation semigroup capital T with speed c, okay, the function where Tt of x, okay, Ttx a was defined as x of a plus ct. Okay, so this if this is the semigroup, so here what is x? X is a function of real number. Okay, and so the Banach space what you choose is here possibly we can choose continuous functions, but however we don't do that. We take yes, if we can first take that space of all continuous functions, but then the generator, the inference generator of this semigroup turns out to be a differential operator. So that is not defined on the whole Banach space. So there we need to take a smaller subset here. So here what we have already seen that the derivative ddt of tt of xa is equal to c times dd, so I mean dda of tt of xa. So here this derivative is with respect to this variable small a. Small a is real number, and x is what? X is the function. Okay, so here with t of 0 is identity operator. T of 0 xa is equal to xa itself. Okay, so this is a function. Okay, x function. Okay, so where x is now, if we choose x in the domain of the generator, so the generator is this differential operator. So if x is differentiable, okay, if x is continuously differentiable, that is in the domain of the generator. Okay, so then already that this dgt of this this ttxa, which is unknown here, we can imagine that way, and then that equation is satisfied by this solution, that x of a plus ct. Okay, so that is the solution of this Cauchy problem, where this is actually a partial differential equation of first order linear partial differential equation. So here this function is a function of t and a variable, okay, two variables. So here we have partial derivative with this t. Here I did not write down partial, I mean like del operate notation. Why? Because this was understood as ddt of x, so in the space of vectors, and then evaluated that at a, so that way. Otherwise, if I would like to, and here ddt xa, so if I now write down this as a function of two variables t and a together, then I should write down this as a partial derivative with this to t and partial derivative with this to a here. So that is anyway a translation PD, and for that the solution is that x of a plus ct is the solution of this equation, where t is running from 0 to infinity. Okay, so that is the discussion I wanted to make, so that with this example we are recollecting that already we have seen some glimpse of such equations, and we have seen solution of this equation, and so here only for a general case we have proved this theorem that whenever we have an operator A which we can identify as infinitesimal generator of a C0 semigroup, and if in that case the initial vector is also in the domain of this operator A, then the solution exists and the solution is written as Tt of x. Okay, so let me conclude this lecture here. Thank you very much.